Hello there. Um, let's continue with our study and let's move on to our next topic. Once we're ready with the basic function calculations, let's start to take a look to the limits and continuity topic. This is very important because the limit concept is the backbone o la columna vertebral del cálculo integral diferencial de una variable multivariable. In this case, the limits and continuity is the foundation to solve all your future engineering problems. So I want this to be clear enough to all of you. Maybe some of you are studied this in the past. Um, anyway, we need to do a little refresh on this in order to not have any concerns, any problems in the future. Okay, so as a first step, let's consider this function f of x equals x squared minus x plus 2. Okay, and I'm plotting this function here. This is an approximation of the plot for this function. And as a first step, let's calculate the value of the function for x close to the number 2. What I mean with close? Well, we are going to calculate the value of the function evaluated in numbers close to 2 but not equal to 2. So that means that calculate the function on evaluated in 2 is not allowed in this exercise. Why? Because in the future we are going to see clearly why we are doing this. Okay, so for now, by now, let's think that we need to calculate the function in values of x that are close to 2 but not equal to 2. Okay, uh, one of the strategies that some of the mathematicians did to do this is they chose an arbitrary, this is an arbitrary number, uh, over and under the desired value. In this case, our target value is for equal approximating a number 2, but not equal to 2. So we are going to choose, let's say, 4 values. And as you see here, these 4 values that I'm showing in this table, I am tabulating the function. This is the tabulated form of the function. I am choosing, or I'm picking 4 values from the right. What I mean with from the right is that if we have this plot, this is the target value. We need to know what's the approximation of what the number of the value is when x equals 2. And what I'm saying that from the right is that am I approximating from the right? So yes, okay, this is right. Or from the positive zone of the axis. That means from the right. And this is from the left. Okay, so I am taking values less than x, in this case 1.95, 1.96, 1.99, and 1.999, and I'm approximating the number from the left. Okay, so Why I'm approximating from the right and from the left? Well, because I need to know, in this case, it is clear for me that this function is continuous. What I mean with continuous? Well, that there is no broken points on this line. All this line is a single piece line, and there is no interruption or discontinuities in any point of this line. But sometimes I don't have this plot, or I have a more complicated function, and there is no way to see it in a graphical way or a geometric way. So I need to use this strategy to approximate the function from the left and from the right, just to confirm that I have function available from here to here and from here to here. So one way to validate the continuity of a function is when I approximate the number from the left and from the right. Okay, so that's the reason why I'm choosing these two ranges of values from the left and from the right to approximate the number that I want to know. Okay, uh, once I once I have chosen these numbers, if you see, I am taking 2.05, which is 0.05 greater than number 2, then 2.04, 2.01, and 2.001. And then from the left, I am evaluating the function and 1.95, 1.96, 1.99, and 1.999. Okay, how I am doing this? Well, I am explaining an example here below. Let's say that I want to evaluate the function in the value when x equals 2.04. So this is the function x squared minus x plus 2. What I'm doing here is that I want to know the value of the function f at 2.04. So the x is the variable. So now the variable will be 2.04. So I am doing a substitution here. I am replacing the x by the 2.04, applying the rule, which is squaring up this number minus x, which is 2.04, plus a constant value independent term 2. That is equal to 4.1616, which is the result of squaring up this number, minus 2.04, which is the value of the single variable, plus 2. And that is equal to 4.1216, which is the number that we have here. Okay? So this is a little explanation of what I have done here. And then if we repeat the exercise for each one of these values of x, we come up with this result. So from these 10 calculations, we can observe that when we are approximating more and more from the right and from the left to the value of 2, the value of the function approximates the number 4. Okay, so what's our next step? Well, what we are doing here is we are approximating the value for that function. Let's write some lines here, and let me write another one here. Okay, so what we are doing here is that we are calculating the limit of this function. Please take in consideration that when we say that we are calculating the limit of a function, when approaches any number, we are assuming that that function is not equal to that number. So we are giving numbers close to the value of the variable that we are evaluating. So the notation for this is the following. So this is the limit for the function x square minus x plus 2 when the variable x approaches 2, in this case, equals 4. Okay? And the definition, the formal definition for this is that is the limit of the function when the x value tends or approaches to a value of a. In this case, the value of the function will be equal to a number L. Okay, or f of x equals a number L as x approaches a, but in this case, x will never be equal to a. Okay, so this is the formal concept of the limit. There are some other details that we need to consider, but by now this is enough to um, to solve. So in this case, let's see that this is f of x equals 4 for our first example. We already approximated from the right and from the left to determine the value of the limit. So this is the way that we approximate a function to a limit value. Let's do another example. Let me save this and let's write in another board. Let's have another board here. Let me erase. Let me have this open. Let me open another board here. Let's do another example. Okay. Um, let's let this f of x be um, x minus 1 divided by x squared minus 1. Okay, um, this is the a quotient function, and let's see that we need to calculate the limit of this function when the value of x approaches 1. So if we do this, substituting the n, the number of 1 on the function, we will see that if we have this 1 minus 1 divided by 1 squared minus 1, that is equal to 0 over 0, and this is an indetermination. So this is indeterminate, and that we are not allowed to do this. So how can we proceed to solve this problem? What's the limit of the function, or what is the value of the function when in this expression x equals 1? Well, if we do this geometrically, we can see clearly what is the value of the limit. But how can we do that analytically? Or how can we calculate analytically the limit? Well, there are two choices. One, if we approximate the function from the right and then from the left, we can say that let's choose a number of x. Let's see, 1.001. Let's take the number from the left. Let's say 9.999. Okay, and let's do the calculations there. If we perform these operations, we will come up with this number, let me do a little bit here of x minus 1 divided by x squared minus 1, and let's have the number, and let's see what's the value of the function when equals 1 over 1. Okay, for this f of x will be equal to 0.4997, and if we evaluate the function in 9.999, that will be equal to, no, I'm sorry, this is not correct. Let me change this. Let me change this to 0, because has to be 0. This is 0. Okay, if we change that to 0, then we have the number of 0.55002. Okay, this is the value of the function of x. Okay, um, approximating from the right, we can see that we add this little tiny delta to 1. We can see that we come up with 0.4997. And if we approximate from the left using this less than 1 value, but with a tiny difference, we can see that yields the number of 0.5002. So from here we can, by intuition, say that we are approximating a value of 0.5. Okay. So even if I cannot do this approximation substituting the 1 in the x value, because there is an indeterminate operation there, if I approximate from the right and from the left, I can see more or less what's the value of this function will be when x approaches 1. Okay. Another way to do this is to factorize, in this case, the expression. So our function is equal to x minus 1. Let me erase this. X minus 1. X minus 1 divided by x squared minus 1. So I can keep this x minus 1 here, and let me factorize this one. If we factorize this one, we can say that this is equal to x plus 1 times x minus 1. You remember this from your algebra classes in the past. If you do this operation, you will see that this is equal to this. So from here, I can cancel out this one with this one, and this will be equal to 1 divided by x plus 1. So this and this are the same. The only difference that I perform factorization to this denominator just to get rid of the indetermination in the function. So now, if I substitute in this case the number x equals 1, that will be equal to, in this case, is 1 over 1 plus 1, and that's equal to 1 over 2, and that's equal to 0.5. Okay, so this is the two ways that we can apply to calculate the limit. If you do these direct operations, sometimes it's not going to be possible. So in this case, we used the factorization to come to the result. And you can also have or calculate approximations from the right and from the left to see what the number tends to be when we are getting closer to this limit expression. So I am expecting this to be clear enough for you. And please, if you have any questions or something is not clear, please let me know. I'm expecting your answers and comments so I can support you in this new topic. Thank you.